You have to tell me what it is because I can't find my study guide. Yeah, so what'd you come up with for that one? That's more how they're transported around. So what does your body do with lipids that you eat is what it's asking. So you can break it down for energy, store it as fat. So break it down for ATP, store it as fat, and you can use it to build other stuff, basically, like steroids and whatnot, or phospholipids.
List the two main sources of cholesterol?
Yeah, so two main sources of cholesterol are diet and liver.
I have two different after.
What did you have?
I had diet and liver and then food and family.
Oh, so it's talking about like the genetics of your cholesterol level, but in terms of like from in your body, yeah, what you eat in your liver. That's what I was getting at there. So it's to transport cholesterol and triglycerides around the body. Yeah, it's like move cholesterol and triglycerides around from one tissue to the other. It's not there to clog your arteries. It's not what it's there for. Well, LDL does, but that's not what it's used for. It's supposed to do, I should say. Turn this light off. All right, let's take our quiz then. All the sniffling over here. A few of the quizzes, the number 5, D got cut off. So D is all of the above on number 5. If you've got a quiz that's slightly sliced, y'all's are fine. So D is all the above for 5. I don't know. Oh, if it got cut off. Yours are fine. All right, so then pass those on up when you're done. All right, so what does a lipoprotein have in it? Is it lipids, proteins, glucose, or lipids and proteins? It's lipids and proteins, as in its name, lipoprotein. What's it called when you make lipids from glucose? So is it glycogenolysis, glycogenesis, lipolysis, or lipogenesis? Lipogenesis. You probably could have just figured that out from the genesis part of the word and go from there. What's not a source of cholesterol? Diet, liver, or skeletal muscle? Skeletal muscle. Let's see, which of these is not a factor that affects your metabolic rate and heat production? Exercise, body temperature, age, or all of the above? All the above, exactly. And difference between minerals and vitamins. It's vitamins are organic and minerals are inorganic, which means vitamins were made by a living thing. Minerals are just like pieces of rocks. Don't ask me the difference between rocks and minerals because I don't remember. It's something my wife teaches her third graders. I can never remember it. What is the difference? Minerals and rocks? Right now? No. Oh. I guess we're not smarter than third graders. We finished part 1, right?
Yeah.
All right, we'll see what we need to do still. I don't know which of you to trust. So. Here, we probably had something to do with ATP synthase or something. Oh yeah, I told you we were going to do a few things. Yeah. Let's see, what was it? We were going to do this demonstration, and there's one other thing I said we were going to do. We did all that. We didn't do this slide either. Okay. All right, so this is about what your body uses ATP for, and then sort of how you recreate it, how it's remade. So most of this chapter, so everything from part 1, were we using ATP or were we creating it? What were we mostly doing? We're creating it, right? So that's this left side, which is a catabolic reaction, which is like all those steps that everybody did of breaking down glucose piece by piece. You were breaking it down, so that's catabolic. And that released energy, which we used to add a phosphate to ADP to make ATP. So that's this half. And then what does the cell do with the ATP? It uses it to turn simple molecules or monomers, like amino acids or fatty acids, into more complex, larger molecules like proteins or glycerol. And that takes energy, so it's anabolic, which means you break down ATP. You break off a phosphate to get energy to build all those things up. So that's basically that thing in the study guide, the role of ATP in anabolism and catabolism in the cell or whatever. That's what we're talking about. Catabolic reactions make ATP, anabolic reactions use it up. All right. So I need some help with this one. Let's see what we use. Got 2 bouncy balls left. All right, let's use some Play-Doh. All right, can y'all make some balls out of those? Other colors. Yeah. Yeah, I'll make some balls out of that. See your Play-Doh skills. I already made some, I guess. Let's make 3 out of each container.
Oh, you already have the balls ready?
Oh, I guess I started those.
Yeah, you did.
Well, you can polish them up. Make them nice. All right, let's see. And then we'll also need some volunteers too. That's what color is it?
I don't know.
You don't know what color your room is? No?
Chose it.
I think we painted our house like snowstorm or something. Something with snow in it. I don't think she's too interested. All right, so we're going to need some volunteers to do this. And basically, we're going to be a mitochondria. Specifically, in this room is the matrix. That wall over there is the inner membrane. So then out there is the intermembrane space. And then like outside is the cytoplasm. So that means that's, one more wall would be like the outer membrane. Let's see, so we can make we'll make the blue Play-Doh, H+ ions. What's the other? What color is that?
This is like a orange teal.
Okay, I can't spell turquoise, so I'll just write teal. All right, who wants to be, I need 2 people for the electron transport chain. Tom, tom, tom. All right, we got 1. It's all right. I'll wait as long as I have to. Who else?
I feel like everyone's going to be doing so this year.
All right. So that's our ETC, and then we need an ATP synthase. All right. What do you say? Do we need anything else? All right. And I'm just the director, I guess. Oh, these bouncy balls are the electrons. And I'll be the NADH. Because, I'm so talented, I can be the director and the actor. And they'll play at the same time. All right, so I guess we need everybody, we need our actors to come up here then. And it's probably all in the back. You probably want to stand up too, because we have to use this doorway. I don't think you'll be able to see what's going on from back there. All right, so we're going to start with our electron transport chain people over by the door, because they're supposed to be in what membrane?
Intermembrane plate, right? For the hydrogen.
Oh, sorry, but you as the chain, you're the inner membrane. So you're in the doorway, standing there. Yeah, you're throwing things. Let's see, what's our oh, blue. So we need all these blue ones. Whoops. Whoops. Okay, so these, where do these H pluses start out? Intermembrane or matrix?
Matrix.
Yeah, so they're just kind of hanging out. They're just in here in the matrix. Where do they get electrons from? Do they just find them, or does someone bring them to them? Who brings them? What molecule? The what? H plus has no electrons. That's why it's a plus. What were you giving electrons to in all your steps? You gave to some molecule that gained energy. What? Not ATP, the other one. NADH. That's me. So I've got the electrons. We took them out of glucose. And now we need to do something with them. So I get to bring them over here to our ETC. And first it goes to ETC complex 1. So you use their energy sum and you toss some H pluses out there. The H pluses, not the electrons. Throw them out there. Okay, there's a few. And then you pass along the electrons to the next person in the chain. Toss them out there.
Yeah, all of them. I was just waiting for someone to come by.
And then, I guess we need, what happens to those electrons now?
No, they go out. They go out.
Not the electrons. No, that's the H pluses still. Because those are the blue balls you threw out there. What happens to those electrons? I remember. They actually lost their energy now.
Is it Marty's turn?
Yeah, the baby count.
No? So they get made into water. So oxygen comes over. I'll be oxygen too. Here, give me some electrons. Thanks. And now I become water. Oxygen, hydrogen, electrons makes water. And so now another NADH can come over, give them more electrons. They can toss more H pluses out. So we haven't made ATP yet. So now we get to. So what happens next? So our ETC is done. You can give them a round of applause. Good job. You can get out of here or come back. So then we need our ATP synthase. Well, where does the ATP synthase sit? In the inner membrane? So where do you think she should go?
Into the hallway with the hydrogen.
In the hallway or in the doorway?
In the doorway.
Right? Okay. I'll have to help her a little bit since y'all threw all those things all over the place. People are probably wondering what's going on. Nothing to see here. All right. Hold on. Let's grab somebody else. Here, Ross, you be in charge of the phosphates real quick. All right. So our ATP synthase gets to what reaction is Marty going to do? Turns, and what reaction does it catalyze when it's turning? Okay. So that means there's ADP and phosphate just floating around here and here in the matrix, which Ross will hold on to us for. So he's got an ADP, right? It's like two balls, and then there's one just hanging out. So we're going to push some H pluses through our ATP synthase and have her spin around. And as it's spinning around, you hear those? So spin around, throw them in here. Throw them in here. There we go. Keep going. All right, and after 3, you've created enough energy to smash those together. So pass them over there. So we've got 2 phosphates. Toss the rest of the H pluses in here. And you smash all those together. And now we've got an ATP, which is our 3 phosphates together. Like so. And then the whole process just keeps going. All right. I think we have a future as actors and directors together. You want to? We got a nice camera here. We can record all these demonstrations, put it on YouTube, get you famous. Be fun. All right. So if you're getting stuck, because this, I don't know why, but this is where people usually get stuck, is the electron transport chain. As you saw, it's like hard to keep track of H+, phosphates, electrons. It's all this stuff to remember. NADH. So you can think of that. You can even practice at your house. Go stand in a doorway and get some Play-Doh out or something. Yeah, if you've got kids or roommates, you can make them be in your play even. Your parents. It'd be funny. All right. This one ended up with a staple in it. That's dangerous. All right, let's see. Did we do all those questions? Did we do this question? I think we were waiting for this one. Cool. Oh, and we could put our Play-Doh up before it dries out. I left it out for an hour last semester, and it dried into, like, crust. Sweet. Wonder if we left any out there. Where's the other blue one? Do y'all have a blue one?
No.
Oh. Ross took all the blue. Oh, all right. I have to think of something else we could do with the Play-Doh. Alex. Notice it does say which is false. Make sure you're answering the false one. How many people are here today? 3, 6, 10, 12. All right, a lot of answers. So why don't you talk to your group about it? Let's see. Steel Play-Doh. They're just ignoring you. All right, we got 20% A, 70% D. The answer is A. Wait, I already forgot. Were you the ATP synthase, Marty? Yeah. So what went through you to make you spin? Oh, you don't remember?
It was
You're such an actress.
cluster.
No? H plus. H plus went through there. So it uses H plus going from high to low for fuel.
Yeah.
Right. So electron transport chain people, they used NADH for fuel. So if you're following like where the energy goes, starting at the whole beginning, you started with glucose, and you took its electrons out and gave them to who got its electrons? So most of its energy gets transferred to NADH, a little bit of it to ATP. What happens to the energy in NADH? What? That's what happens to the electrons in it after you use their energy. But what did you actually use the energy for? Which? Yes. So H plus.
And then that made oxygen.
H plus concentration gradient. And we used, because that's a form of energy, right? Like potential energy. And you turned that energy into not quite. What's the whole point of all this? What are we trying to make? There you go. So if you're following along of like where the energy went, it started in glucose. You took some of it out to make ATP and NADH, and then you use the energy in NADH to pump hydrogens, and you use the energy of having more H pluses out to make ATP. So if you're trying to simplify like where the energy is going. So it's like 1, 2, so it's like quite a few steps there. Now the reason we do it that way ourselves is because that's how it evolved to be as efficient as it possibly could. It's not to make your lives hard, why it's so many steps. It's just, and how efficient is this? Do you remember what percentage of energy you get out of glucose? It's 40%. Or 40%. So you get 40% of the energy out, the other 60 is lost as heat. Or creates heat. The other 60 becomes heat. Which is going to be important for part 2. Whoa, is that thing getting darker? Uh-oh. What are we going to do if our projector goes out? It's going to be the end of the world. All right, why do you lose 2 to 3 pounds when you're asleep?
Does that have to do with your metabolism?
Your metabolism, but I mean, atoms, molecules, they weigh something. So how are you losing those? Where are they going? But heat's not a molecule, that's like energy. They have to be leaving your body somehow. Hey, if you drool 2 pounds of drool every night, that's your own problem. So respiration, that's very close. Okay, so well, do you think you lose water vapor when you're breathing?
Yeah.
Okay, that's a small part of it, but not the major part. And yeah, if you're sweating, obviously you're losing water weight, but that's not the major part either. There's something else. Okay. Yeah. So you break down glucose. What does glucose turn into? ATP, NADH. But what are the carbon atoms turn into?
CO2.
What happens to CO2?
You breathe it out.
You breathe it out. Yeah, so that's where you lose most of your weight at night, is breaking down, because like you said, metabolism, cell respiration. You're breaking down glucose into CO2. You're breathing out CO2, which weighs something, right? Because it's got 3 atoms. It's pretty crazy. So I'm going to start my new I'm going to write a weight loss book called Breathing. That'd be awesome. So we're going to have some activities of like you got to breathe faster. I'm telling you, it's no sillier than the other one. And for $300, if you give me $300, I'll tell you could be like get on the ground floor of this business.
You're like, the goal is to sleep 16 plus hours, people. 16 plus hours. Don't worry about exercising.
You just have to sleep. All you have to do is sleep and breathe
And not eat.
and not eat. That's the other important part.
Don't worry about none of that.
All right.
Keep hydrated, then you need that water.
It's true. All right, so let's do part 2 then. We've moved on from all our molecular stuff to get to the body. This is on the bold part of the study guide, right? So you did all these already. Just talk about a few. Your metabolism does go up when you eat to get ready for breaking down all that food, making all those enzymes, stomach acid, which is why, do you get cold or do you get hot when you eat? Especially if you eat like a whole bunch like I did on Sunday at the Indian restaurant. You're just like shoving food in your face and you're like, I'm just so hot. That's why. And also, if you have a fever, it actually increases your metabolic rate. Does anybody know why that is?
Body's trying to make energy to fight that infection.
It actually has to do with enzymes performing faster when they're warmer, at least slightly warmer. So all your metabolism just starts to go faster if you're hotter.
Is that why sauna works? Not only the sweating, but your heat
In theory, yeah. Yeah.
or sweat.
I didn't thought of that, but yeah. I mean, if you make your body temperature higher, you're going to burn energy faster.
Well, like a lot of wrestlers will do this stupid
However, what works even better is to make yourself extra cold.
Really?
Yeah, I was gonna say, I don't get, when I get like sick, I don't get fevers, my temperature doesn't go up, it actually drops.
Well, you might have a problem with your hypothalamus.
Yeah. Well,
Is your body temperature 98.6 or is it something different to start with?
I'm always at 97.5.
Huh. So you kind of start lower. Interesting. I don't know. You've never gotten a fever from being sick?
No, I'm trying to call into work because I was sick, it was really hard. 'Cause they
Yeah.
were like, come in so I can check your temperature. I don't get a fever.
Downside of it.
Huh. That's interesting.
I got it going on.
And that's
So why does being cold work?
so if you're cold, which we'll see in a little bit, your body has to make extra heat and break down more food.
So, yeah,
Not even just shivering, but like just breaking down your food faster.
I'm always cold.
So that's the other part of my weight loss plan is turn your thermostat down and sleep without blankets.
Ross, there you go. There's fasting, and now you need to tell your wife that it needs to be below a certain temperature.
Yeah, you have to get an air conditioner for the summer. All right, so what about lipids? They're obviously hydrophobic because they're fats. So that's why they have to get transported in lipoproteins, which we'll see right there. So they're mostly phospholipids, except it's not like a cell membrane where you've got 2 layers. You've just got 1 layer. So the hydrophilic part of the phospholipid sticks out, and then the hydrophobic part is in the middle. And then you've got all the triglycerides in the middle. Cholesterol is on the outside, along with the different proteins that are used for binding to the target cells. So that's a lipoprotein. And the difference between the 4 different kinds is the percentages of triglycerides or cholesterol that they contain. And I guess I should point out cholesterol is something all your cells need. It's in their cell membranes. They use it to make steroids as like structural molecules. So cholesterol is not like just a bad thing. It is something your body needs. But if you have too high cholesterol, that's when you can get problems. All right, so LDL has 75% of the cholesterol, and it brings mostly from the liver to target cells, which is basically all the cells in your body need some cholesterol. And HDL does the opposite. It goes around and looks for extra cholesterol in the cells, picks it up, and brings it back to the liver, and the liver can get rid of it. So there's things that have cholesterol in it. You probably knew that already, right? Eggs, meat, cheese, things like that. And of course, cholesterol was demonized for a long time. Probably still is somewhat. But less than it used to be. So I can remember, like, what is it, 20 years ago, maybe 15? They told everyone, like, eggs are bad for you.
Everything.
Yeah, fat's bad, but especially cholesterol is bad, so you can't have eggs. Or, sorry, egg yolks, right? Because egg whites don't have cholesterol. So you have those, like, egg white omelets, or people just eating the egg whites. And that's because the higher your LDL cholesterol is, the higher your chance of having heart disease. And that's because the more LDL you have, the more of it gets sort of deposited in the arteries, causes inflammation, and then eventually you get these big buildups of inflammatory cells, etc. We'll talk all about in patho if you take patho, but they block the blood flow, and they can even rupture and create like clots, lead to strokes or heart attacks, or just angina, which is like chest pains from low blood flow to the heart. So HDL is good because HDL takes extra cholesterol out and brings it to the liver, which is why LDL would be bad, or usually we call it the bad cholesterol number, and HDL is the good one. All right, so here's some data for you. So if they just compare people's LDL levels, which is on the x-axis from 40 to 180, and then the relative risk of having either a heart attack or a stroke. The lowest levels, that's like kind of the baseline. And then as you increase up to 180, you're 3.7 times more likely to have a stroke or a heart attack if your LDL levels are that high. So that's what led to all that diet discussion of what you should eat, and then also development of drugs like statins. So if you ask your parents or grandparents, I bet a lot of them are on statins. So they're pretty effective at lowering your LDL levels. They actually prevent the liver from making so much. And you can see that on here, each of these green dots. So like 4S, this is a study where the people who had the placebo pill stayed at 190 LDL, and they had a 30% chance to get a heart attack or a stroke. People on the statins went down to 130, and they went down to a 20% chance. And then this study, basically you can see all the studies they did, you had a decreased risk of, or lower LDL and less of a chance to have a heart attack or a stroke. All right, what do you think the main contributor is to somebody's cholesterol level? All right, so go and chat with your group then. We'll vote again.
start your diet.
All right. Final votes. All right. The answer is actually B. Which you wouldn't think from all that you hear. And actually, like 70% of your cholesterol comes from your liver. It's not from what you're eating. It certainly has some effect, but it sure seems like when they look at it, you know, it's genetics that's number one. You're either prone to have high cholesterol to start with, or you're prone to have normal or low, and there's not a whole lot you can do about it. Which is kind of surprising. And of course, that's why I do hear as much about don't eat eggs anymore. You don't really hear that from dietary guidelines very often. And that's because they finally kind of tried it out with tons of people. Change your diet. Did it change their cholesterol levels? Not very much. All right. So let's do some metabolism. So your body basically has, you could probably call it like three main states. It's got the absorptive state, which is when you're eating like 4 hours after, where you're absorbing all the nutrients from your food. The second one is post-absorptive, which is after that. And that's you just use your stored glucose or stored fats. And then after, 4 or 5 days, we have a sort of even more extreme state where the body goes into starvation mode. And it's got other sources of energy and other changes it makes. Because as you know, how long can you go without food? Months, depending on how much stored fat you have. As long as you have water, water is like 2 or 3 days. But food, that's why we store fat. It's for that situation, which obviously we're not going to be exposed to, hopefully. But when we were, cavemen, maybe we wouldn't be able to hunt for weeks, and you just have to live off what you ate, what you stored. Has anyone fasted for more than 2 or 3 days in here, or more than a day? Yeah? How long did you do it for?
I did it for a day and a half.
Yeah? Is there any point that you felt better? Or did it feel horrible the whole
I
time?
just felt like I was starving to death. That's because I cared too much about food.
So I talked to a few people who have done it for 3 or 4 days, and they said after 1 day, they just kind of felt normal again. Their body just kind of went into starvation mode, and they had enough energy and food, and they felt fine.
Yes, I had enough energy to do that. I was still wanting.
You're still wanting food. Yeah. I'm sure that's how I would be, but it's kind of tempting to try it just because teaching the chapter, maybe I should not eat anything for 2 days. But I probably shouldn't do it when I'm teaching, because who knows what will happen to me. That happened to me in high school. I didn't eat breakfast, and I passed out and fell out of my chair and scraped my face on the floor. It was very embarrassing. I had to call my mom to pick me up and come to school with a scraped face. It's really, really embarrassing. What happened? You're oh, never mind. Yeah, I know. That's terrible. All right. Let's see. What are y'all doing? All right. So I'm going to pass this out for you. You probably saw this diagram in your book. It's comparing metabolism during absorptive and post-absorptive. So I've got one for you. And you're going to use it to answer these questions. It's a bunch of statements, and you have to tell me whether that's absorptive, post-absorptive, or both. Just based on this diagram. This diagram is all you need. So feel free to work together on that one. So, she was here last week, wasn't she, Alex?
She was on Thursday, Tuesday.
She wasn't here on Thursday either? That's weird. I saw her yesterday.
She wasn't here Wednesday either.
I wonder if she dropped.
Yeah.
Yeah. Huh. I have to. Maybe she dropped the class. I'll check on it. Alex? Should have been here for like 3 days. Oh, here's the statements. So question 1. There's lots to choose from.
Thank you.
Is there an extra one for me so I can answer them too? Make sure I remember the answers. Yeah, so all you need to use is that diagram. That's the only thing you'll need. Boom, 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 boom.
Go to multiple amino acid and then into the blood. No, because it's not in the post-structure of it. It's not in the liver. There's only a.
Lessons.
Would it be post again? As well, and liver? It doesn't have it. I'm not looking at that. It's only for egg. Because abajo it's not in the
Yeah, but it doesn't look like a
So you're in this state right now, Ross? Sure you don't want a delicious like breakfast burrito right now?
I worked on a 12-hour shift every day since we've been on, so I ate breakfast those days.
Okay.
So today I feel really hungry because I got used to it.
Uh-huh.
Oh, it was the Oh, yeah. Because it's one of the brand that is. What did you say, Eat it.
Oh, yeah, no. I'm right down here.
Wait, no, it's not. Because it's not in the liver. It's not in the liver down here. But it was just egg. But I know there was one that came with that it was No, but we have
This one is both.
You want to do number 2?
No. We're gonna talk about the feedback thing a little bit.
Cool.
Yeah.
Well, there's no other there's triglycerides. Okay, triglycerides into the heart, fatty acids into the adipose tissue as fatty acids is coming into the bloodstream.
Yeah, over triglycerides, you stay triglycerides.
So there is one that's both on there. Oh, you got one? Oh, I didn't see that. It's not that one. No.
I think it's 8.
But there is a different one. See if you can take a guess.
And then into the, so that one has to be 8. So it has to be the C one that's wrong.
I wonder if C is 8.
Okay, you're saying it's A?
You're right.
Yeah. That doesn't make sense. Like I have to read what it is.
Yeah, it is P8.
All right.
Yeah, because right here I can break down. Again, they're all gonna be wrong.
All right, so let's go over those, see if you got all of them. So glucose is absorbed from the GI tract. That's A. It's absorptive. Skeletal muscles break down proteins. That's PA. So your skeletal muscle actually can break down, I don't know, a third of its protein without affecting its function. So that's an important storage area. Triglycerides are formed. That's A, absorptive. Skeletal muscle breaks down to get glycogen. Breaks down glycogen to get glucose. That's PA. Glucose is turned into glycogen. That's A, absorptive. Liver converts fatty acids into ketone bodies. That's PA. Heart and nervous tissue use ketone bodies to make ATP. That's PA again. Glucose is used by tissues to produce ATP. That one's both. I think that's the one that's not completely clear in that bottom diagram. But if you notice, you're putting glucose into the blood from the liver. You're doing that so that your cells can use glucose. But you also have those other sources, because maybe your glucose levels are lower than when you're absorbing food from the intestines. So it is both for that one. Excess amino acids are turned into fatty acids. That's A. It's absorptive. Let's see, liver breaks down glycogen to glucose. That's PA. And triglycerides are broken down into fatty acids and glycerol. That's PA as well. All right. So did you notice that everything you ate can end up as triglycerides in that diagram at the top? So if you eat a bunch of fat, they just go straight to the fat tissue as triglycerides. If you're eating extra glucose, where does it get turned into triglycerides? In the liver. So you can see in the middle, glucose gets turned into fatty acids and triglycerides, and then those triglycerides go to the fat tissue. So even if you eat no fat, you could still get more fat in your fat cells. Same thing with the amino acids. What happened to them? How did they become triglycerides? Based on the diagram. So if you look at amino acids, they get turned in the liver, they get turned into keto acids, which are turned into fatty acids, which are turned into triglycerides. So everything can be turned into triglycerides if you're eating too much of it or eating extra. So I think an interesting idea about this one, how many of you go like more than 4 hours between eating anything, including anything with sugar in it, any drinks? So if you're not, aside from when you're sleeping, but during the day, if you're never getting into 4 hours after, that means you're never getting into post-absorptive. So you're never going to break anything down. It's always going to be constantly, absorbing and storing until you're sleeping. So I think that's one of the reasons that, like sugary drinks have such a profound effect on people. So anyways. Something to think about. Oh, and the one other thing is you've heard of insulin, I'm sure. So insulin responds to high glucose, and one of the main things it does is tells the liver to take all the glucose out of the blood that it can and turn it into fat. So that means the higher your glucose spikes up from eating sugary things or simple carbs, the more fat you make in your liver. Because high glucose levels are damaging to the body, so insulin responds very quickly, and they just turn it into fat right away. It's kind of interesting.
Anything else?
Do what?
Yeah.
So taking a look on there, it can turn into glycogen and skeletal muscle and turn into fats in the liver. But the higher the level is, the more triglycerides you make from it. And so that's why you're seeing more and more those dietary changes. They're getting away from, you need to eat low fat, and now it's sugar's bad.
My brother's a fitness model out in LA.
Oh yeah?
And he read a book recently, Eating Fat to Stay Skinny. And he will drink whole milk and all this fat, but doesn't eat any sugar.
Yeah, that's what some people are trying. Probably seems to me that maybe you want to balance it a little.
Right.
But yeah, it's interesting. So fitness models, so does that mean he exercises a lot, or he just
He works
takes his
out,
clothes off and
4 hours every day,
yeah?
regardless.
That's crazy. Well, it's his job. He just has to look good, I guess.
He's a flight attendant, so he's always
Oh, really?
on a layover at some hotel. He's like, well, I guess I'll just work out there.
Wow.
My own is too, but she's always on the beach during layover.
Cool. Oh, Bree, what was your question?
What would you do if you had high triglycerides?
Do you mean like circulating in your blood, like high LDL or something? So they would recommend people have tried eating less sugar because then you have less triglycerides, or there's things like statins, like drugs that'll lower your triglycerides / cholesterol levels. Anyways.
You know what? You're going on a new starvation plan?
Sorry, we'll have extra time next time. But my favorite thing I just heard, who do you think's more likely to gain weight, people who diet or people who don't? People who diet. It was just another study that came out. So people who have never dieted have less likely to gain weight than people who try different diets to lose weight and stuff.
It's people who try diets are fat.
No, that's not why. They adjusted for it. That's rude.
Is it because they think about it so much? Like they
I think it's because your body doesn't like switching to make these dramatic changes from here to here. So the only thing that's really effective, and actually exercise isn't effective either for permanent weight loss. It's small changes in diet that you can stick to that matter. Or just eating healthy to start with. It's kind of interesting. Of course, you wouldn't have all these diet industry things if all it was eat healthy and don't eat sugar and whatever.
Cure cancer and every other disease.
Maybe. All right, so moving on. Sorry, pet peeve there, like reading about diets and metabolism. I think it's interesting. So moving on to our metabolic rate. What hormone regulates your metabolic rate? Primary hormone. What would you say if you had to guess? All right. So C is the correct answer. This thyroid hormone is the primary hormone that controls your metabolic rate.
Over 65 on levothyroxine.
What?
So that's why everyone over 70 is on levothyroxine.
Is that thyroid hormone?
Yeah.
Yeah. My grandma's on it. I even had a friend who put their dog on thyroid hormone.
That's
So their dog was old and feeling tired. So they're like, here's some thyroid hormone so you have some more energy. Nobody else has put their dogs on thyroid medicine? No. Well, it'll be later.
my dogs have puppies. It's not enough energy.
Well, yeah, puppies don't need extra. All right, so metabolic rate, what is it exactly? Basically, it's how fast you do cell respiration. So the first part of the chapter, how fast you break down glucose into ATP. That's what metabolic rate means. And so when someone says they have a slow metabolism, what are they saying? So slow metabolic rate, and they do cell respiration slower. So they're not going to break down as much glucose as fast as they would otherwise. And if you're just measuring it at a steady level where you're not exercising, you're not eating, that's called your basal metabolic rate. So different people have different basal metabolic rates, and it changes based on gender, based on age. And one of the things with exercise is it does increase your basal metabolic rate afterwards, after you're exercising. Why do you think an increased metabolic rate causes you to get hot? Production of ATP generates, right? So like the more glucose you break down, the more ATP you make, but it also makes a lot of heat in that process. Did anybody read about the one exception to that? That there's a way your body can make heat without doing this process? No, that's actually shivering, the interesting one. So shivering just means your muscles are contracting, so they need to break down more glucose, which makes more heat. It doesn't actually make you warmer. So infants have a special kind of fat that just turn glucose almost directly into heat, called brown fat. Because they don't have as developed of thyroid hormone and all these other mechanisms that we use when you're older. So I think it's, up to like 6 months of age, they can just even they've got this special tissue to just keep them warm, basically. So as long as they're getting enough food, they could stay warm a lot easier than we can. Which is interesting, because what do you hear from your parents if you had kids? Are they always worried about your baby being cold?
Yeah.
Probably don't need to worry so much. Because I know our daughter, we took her camping when she was like 4 months old. She threw all her blankets off, and she slept with pajamas on when it was 50 out. She was fine. She was hungry, but we were so worried. We woke up and put blankets on her in the middle of the night. She threw them off again. So long as they're not super premature or something, they're pretty good at making enough heat for themselves because they have that special fat. Brown fat. And actually, we have it too. They found out 3 years ago. Back here, back behind your back somewhere, and I think a little in your neck. So they did a study where they were able to do scans and see when it lit up. And so they showed people in a cold environment, real cold, staying in a 40-degree room for half an hour, and your brown fat turns on, breaks down glucose, makes heat out of it. We don't have very much, but we apparently do have some. We just found out. Yeah. All right, so anyways, let's see how you respond to cold. So I want to point out first, there's thermoreceptors in your skin, but these are not the same receptors that tell you your hands are cold. These are receptors that go to the hypothalamus and tell your hypothalamus that you're cold, which is not a conscious feeling. But you also have cold receptors that tell you your hands are cold, which looks like a lot of you have cold hands at the moment. Everybody's doing those. And you also have receptors in the hypothalamus. They send information to the control center, which is mainly in the hypothalamus. And that causes hypothalamus to tell the pituitary to make TRH. The pituitary makes TSH. Goes to the thyroid to make thyroid hormone. And it also tells the adrenal medulla to make some adrenaline. Sends signals to do vasoconstriction of the blood vessels close to the skin. Why do you think you would do that?
So you quit losing all that heat from your blood.
Yeah, so if you keep your blood closer to your core and less to the extremities, you don't lose as much heat out of the blood, which is why y'all have cold hands right now. So that's one of the, think about if you had lots of blood flow out to all your fingers. You lose a lot of heat that way. So you may get frostbite on your fingers, but at least you're not dead. You stay warm enough for your heart and liver to work. So you don't need all your fingers to stay alive. Right? And all those responses, your body temperature goes back up, hopefully, and the stimulus goes away. So it's a negative feedback loop like we've been working on. Great. So we'll practice some more on this. We're out of time, but Wednesday we've got our exam review. So we'll take 20 minutes to do the last of this. And I was going to tell you how many teaspoons of sugar do you think the average American eats?
Too many.
Give me a number. How many teaspoons?
50.
A day. Average teaspoons of sugar a day.
30.
It's about 30. So one kind of thing you can look at, if you're looking at something you're eating and it says grams of sugar, you divide that by 4, and that tells you how many teaspoons of sugar are in that. So a Coke, 40 grams of sugar, that's 10 teaspoons of sugar. So just try to imagine, I'm just going to eat 10 teaspoons of sugar right now. That's what you're doing. Or orange juice, any of the juices, there's a ton of sugar.